Alrighty. Well, thank you everybody for showing up today for our Introduction to Infrared Spectroscopy lecture. So here it's a dry lab. You have a worksheet in the course packet which you can work on. It will be due 2 weeks from today. You also have a post-lab quiz which will also be 2 weeks from today about the topics that we will cover here. So again, ask me a question at any point. We're going to talk about infrared spectroscopy. What is infrared? What is spectroscopy? What can we actually learn from this? Last week, I took you guys into the hallway and I showed you the machine. I showed you the graph and I told you about the dances, the molecular dances and the yogas and the vibrations. So we're going to get into the details of that today. So let's go ahead and get right to it. One of your pre-lab quiz questions was, what does IR stand for? Infrared radiation. Infrared radiation. We use infrared radiation spectroscopy, but we just call it infrared spectroscopy. So spectroscopy is simply where oops, I don't know what happened here. Can you guys still see my screen? Let me try again. I don't know what happened there. Okay, it's still recording. Sorry about that. Having technical issues here. So spectroscopy is where we take a light and we shine it onto a molecule and something happens. And then that something gets measured and we are able to learn some information out of it. So we have two sensors that we are all born with. We call them eyeballs, eyes. And these two sensors are very good at picking up electromagnetic radiation, which we call visible light. We know this as the rainbow, Roy G. Vib. That is everything that we can pick up. It is 400 to 700 nanometers. You should know this from like seventh grade physics. If you don't, you should know it from high school. If you don't, you've learned it today in college. Visible light is 400 to 700 nanometers. Nanometers. All right. Make sure you know that because anything stronger than violet is ultraviolet. Ultra is a Latin word for beyond. So it's beyond violet, stronger than violet. Anything that is infrared is lower than red. That's what the word infra also means in Latin. So you have above violet and below red. Infrared, ultraviolet. So we have visible light, and immediately to the left and to the right of visible light are these two. We're all very familiar with ultraviolet radiation, especially living in Long Beach. We go outside and we feel the ultraviolet rays of the sun. I know it's considered trendy to tan. You go to those machines and you turn on the UV light, and the UV light burns your skin, right? That's how much energy it contains. Light is in the form of a photon. It is a particle that carries the energy of the electromagnetic radiation. And so these photons have a lot of energy. They move in the form of a wave. And when they have a lot of energy, well, they move faster, right? Think of a sugar rush, or when you wake up and you drink some coffee, you're like, I got a lot of energy, I'm moving around really quickly. Same thing. When a photon has a lot of energy, it has a high frequency. It goes up and down really frequently, right? So it has a high frequency. It's going up and down in the form of a wave. That also means that the length of the wave is small. It has a short wavelength, high frequency, short wavelength. And the opposite is true. When something has a low frequency, when it's a long wave that takes a long time to go up and down, that has low energy. And so visible light from blue to red, blue has the highest energy, red has lower energy, but red has the longer wavelength. All right, they're inversely related, frequency and wavelength. So that means that infrared has lower energy than the color red. Make sense? And ultraviolet has more energy than the color violet. And everything below or above that has more or less energy respectively. So if we keep getting higher energy with ultraviolet light, we get to X-rays, and we are all very familiar with X-rays. They can see through our bones, right? Discovered in the late 1800s. This dude was playing around with a light bulb, and he noticed that when he looked at his hand, he could see his bones, and he's like, "Huh, something else is going on here." Well, yeah, he was getting a lethal dose of X-rays. He lived for a little longer, but that's how they were discovered. Gamma rays are even stronger than that. That's what supposedly gives Superman his strength. The gamma rays interact with the cells of his skin in an Earth atmosphere, blah blah blah. I don't know much about it. I just watched The Man of Steel, so that's supposedly what it happens. But those are gamma rays, very high energy. They're produced by stars. They're produced by gamma ray bursts. They're produced by black holes. And of course, cosmic rays is just anything above that, right? That's what like supernovas and quasars and magnetars and all that stuff give off. And on the opposite end, below infrared, we have microwaves, and we're all very familiar with microwaves. We use them to cook our food. The guy who discovered it, he had a chocolate bar in his pocket and he noticed that it was melting. And he was like, I'm working with something that gives off energy and my chocolate bar is melting. What's going on? So he put it in a box and he shot it with radiation and he was like, oh, this thing heats up food. And now we have microwaves all over our kitchens. And then lower in energy still are radio waves. We use that for the NMR that I showed you in the hallway, the big, giant, bulky instrument. We used it to listen to music. I don't know if you guys still listen to radio. I do. I grew up with radio, so I listen to radio still. I hate the advertisements, but some shows are still pretty good, but the music can sometimes be repetitive, right? You hear Ed Sheeran's Shivers like a million times on the radio in a single day. They only play top 40s. But we used to use that. Also, Wi-Fi. Wi-Fi is a form of radio waves, and I know you guys saw recently that you can use Wi-Fi to find out who's inside the room, how many people are in a room. Well, that's because the wavelength of a radio wave is about the same size as a human being. So it resonates with our size and it's able to reflect or diffract or to change intensity depending on the angle that it hits the human being. And of course, we have, what's called ultra low frequency. We call those ELF, extremely low frequency, ELF. Those are like planet size, like when the whole planet is just rumbling, for you guys who are into the whole the planet is alive, the Gaia theory, there's actually a frequency of 7 hertz called the Schumann resonance, which people claim actually affects all humans and the collective unconscious and the migration of birds and the beaching of whales and all that stuff, right? But it's real. The Schumann resonance is real. It's caused by lightning strikes. They vibrate the whole upper atmosphere, and the whole planet vibrates at a resonance of 7 hertz or so. So yeah, yeah, very cool. Yes, indeed, very cool, right? These things are real. That's what I'm saying. It's all about the vibrations, man. Like these things are actually real. But fortunately or unfortunately, we can only see the rainbow. We cannot see ultraviolet. Some snakes can see infrared. Mosquitoes can see infrared. Some birds can see in ultraviolet. The bees can see in ultraviolet. I wonder if there's something that can see in X-rays, right? Besides Superman, or animals that can shoot microwaves. That would be cool. But anyway, you get the gist of it, right? And all of these waves are described by the equation below. You have c, the speed of light. All of these is light. So there's X-ray light, visible light, infrared light. Radio light, it's all light. It's all electromagnetic radiation. So they are all described by the same formula. C, the speed of light, 3.0 times 10 to the 8 meters per second is equal to the wavelength times the frequency. Or if you want to expand it even further, you can say that the energy of the wavelength in joules would be Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. I don't believe that you'll have to use these equations in your exams, but should be some review from physics or from first semester general chemistry. Light is a wave, and it moves up and down in waves, and sometimes it's a long wave like a radio wave, and sometimes it's a very high wave like a cosmic ray or a gamma ray. So, any questions about electromagnetic radiation? Question, what does the C constant stand for? C is the speed of light. C is the speed of light. So I can just do a quick annotation here. This is 3.0 times 10 to the 8 meters per second. That is C. This is the speed of light. Yeah, good question. You should know that. It's a constant. You can't talk to someone about E equals MC squared and not tell me what C means, right? So yeah, you should know that for sure. All right, any more questions? Okay, so moving on to the next slide. So like I said, a photon of visible light can interact, for example, with my shirt or with your nails or with your eyes. And depending on how it gets absorbed and reflected and refracted, you can see different colors. And so the same thing happens when we shoot different wavelengths at atoms and matter. Sometimes it goes right through. Sometimes it's the same size as the atom or the bond, and sometimes it just vibrates or moves the molecule. So like I mentioned, for radio waves, you're going to use that next semester for NMR to find out how many hydrogens are attached to a carbon. But I won't spoil the surprise. You can figure that out next semester. This semester, we're using IR, infrared, to look at the functional groups vibrating in a molecule, right? So one of the pre-lab quiz questions was, what is something that we can learn from infrared spectroscopy? What functional groups are present? Because the functional groups have specific bonds that vibrate at specific wavelengths. We'll get into that. We also have a type of spectroscopy called ultraviolet visible light, right? Because believe it or not, red light, blue light, it has energy still. And some molecules, you can just shine regular light onto them. So for example, UV light, when you shine it into like a green, you know how the green is glowing? That is the light causing an electron to get excited and and relax and release extra light. Phosphorescence, fluorescence, right? All of that happens in visible light sometimes. So we see that, glow in the dark plastic stars. That's another form of radiation. So I'll explain that in a bit too. But the point is, visible light is also powerful and it has its own effects. I mean, the fact that we can see color at all gives us all sort of information about the materials. So once you get up to like inorganic chemistry, like upper division inorganic chemistry, you realize that color just comes from the chemical bonds in all molecules. So it's really cool, really neat stuff. We use the electromagnetic radiation to learn around the world, to learn about the world all around us, just like we do with our eyes. So, any questions about this? All right. Now, wait, there's a question in the chat. So UV spectroscopy uses ultraviolet light to get electrons to show more light. Yes, yes. So they'll get hit with a photon of UV light, and then they will absorb it and then release another photon of either the same wavelength or a slightly different wavelength. And sometimes you just see that as a reflection of light. Sometimes you see that as, oh, look, a black light on a green thing makes it glow really strongly. That's called like fluorescence. And then if you like take the plastic with the phosphines and you put it close to the light, and then it glows in the dark for like 10 minutes, that's called phosphorescence. That's also the photons being emitted back, but much more slower. Like in a delayed manner, the wavelength is much lower. A whole bunch of physics classes to explain all of this, but this is organic chemistry. But yes, we can use all of the wavelengths to do all sorts of analysis. I took a class last semester. It was X-ray crystallography. We take a crystal and we shoot X-rays at it, and we can find out exactly where all of the atoms are next to each other. We can find out exactly how much one bond measures. So it's really cool. Spectroscopy is very useful. You can make a whole career out of spectroscopy if you really want to. All righty. So we're going to move on to the next slide. So this is what I mean, right? Remember from Chem 111A, you have energy levels, periodic table, hydrogen, helium, N equals 1, lithium, beryllium, N equals 2, potassium, calcium, etc. Sodium, magnesium, N equals 3, potassium, calcium, N equals 4. So the atom has different energy levels as part of the electron system that it contains, right? Electron configurations, 1s1, 2s2, 2p6, 3. Those numbers are energy levels. And when a photon hits an electron at just the right amount of energy, that electron absorbs that energy and uses it to go to the next level. So you could think of it like gas, like having money, right? Like let's say your favorite concert cost $100 and you can't go until you have $100, right? But if you have more, you can not buy another ticket. You can only buy one ticket. You have to have exactly $100. It's kind of like that. You can only go to the next energy level when you have exactly the right amount of energy. If you have more, you can't go beyond that. You can only go to that same energy level. Hopefully that's a good analogy. I don't know if the money analogy makes some sense. I also like to think of a driving analogy. Like imagine only being able to drive in multiples of 5. Like you can only drive at 0 miles, 5 miles an hour, 10 miles, 15, 20, 25. You can never get to 17 or 18. You can only drive at those speeds. It's kind of like this. You can only go to certain energy levels when you have a photon of a certain amount of energy. We call that absorption. So it gets absorbed and then it goes back down to the ground state, we say. It relaxes and it emits a photon of that same energy difference. And so this is why the molecules, the bonds of the molecules, they have the same frequency as infrared radiation. That's why they vibrate. If the molecules were shorter, you could only vibrate them with X-rays or ultraviolet light. If they were very long, you could only vibrate the bonds with radio waves. Technically, you can make a gun that would emit ultraviolet, sorry, not ultraviolet. It would emit some sort of like microwave radiation the same size as a human being, and you could literally just like vibrate a human and then of course vaporize us because you're vibrating like the entire thing. Yeah, this is real. Like radiation guns, all that stuff, like it can get pretty crazy. So fortunately, none of that has been developed. But the point is that you need the same amount of energy as the electron shells in order to be able to have a transition. And so, of course, the higher the energy, the more energy of the photon. So you have what's called, low infrared, high infrared, medium infrared. It depends, just like you have blue versus red. They don't have the same energy. They are both photons of significantly different energy because they are 300 nanometers of difference, right? 400 to 700, there's 300 nanometers between red and green. There can be a difference between one IR and another IR, and they still fall under IR, right? So that's what we're going to look at. We're going to look at a range of IR. But before we continue, any questions so far? Okay. So again, in general, higher energy causes more higher energy excitations, higher energy transitions. Lower energy causes more like pushing and rotating and vibrating, things like that. So we're specifically looking at the vibrations of the bonds. Alrighty, so we get to infrared spectroscopy. So I showed you the instrument, I showed you how it looks. The energy gets absorbed, so you could think of it like a spring, right? I have a spiral notebook right here, right? You could think of this whole spring as like a bond. And then at the end, I have, one atom, and at the other end, I have another atom. And you can vibrate the spiral notebook and you can compress it and you can stretch it. Imagine bonds like a spring, right? In physics, we do this. We call it the harmonic oscillator. That just means a spring. We like to be fancy. And so imagine if you have the same atom, right? Carbon and a carbon bonded together in a spring. Well, the masses are pretty much the same. Well, imagine the masses are different, like carbon and hydrogen or oxygen and hydrogen. The masses are different, so one side is going to vibrate more than the other. All of these have very specific frequencies. They're very specific, they're very unique. So this is why we use IR, because molecules and their functional groups give unique signatures, unique wavelengths, unique vibrations that we can measure. And those vibrations, when we put them on a graph, will give us like a fingerprint of the molecule. And remember, we cannot tell what the entire molecule is, but we know that there's carboxylic acids, we know that there's alcohols, we know that there's something in there. And so we take it and we plot it, and we call that an IR spectrum. Spectrum is singular, spectra is plural, also from Latin. So spectrum is when you're talking about one, spectra is when you're talking about multiple ones. So any questions about this? Again, you see a picture of the instrument. You see here, when I showed you guys in the hallway, I showed you and the graph was upside down, right? Well, now it's upside down again. So this is how we read IR normally. I believe there's a trend where people are starting to read it upside down. It doesn't matter. It has the same information. So you see down here on the bottom right, we start at 400 on the x-axis on the very, very right, and we have 4,000 on the very, very left. And then we have on the y-axis percent transmittance. In other words, how much of the light got through. If 100% of the light goes through, by definition, there is nothing being absorbed. If you absorb nothing, everything goes through. If you absorb something, only a certain amount will go through the compound. And so when you absorb the energy, where does the energy go? It begins to vibrate the molecule. That energy is being absorbed by the spring. And it's like, hey, look, for example, look at this graph. There's like a really big peak at around 3,300, 3,400 on the x-axis, right? That's a vibration that is happening at that frequency. We don't use wavelengths when we're talking about IR. We use something called wave numbers. And if you look over here on the third bullet point, let me see if I can highlight it. Right here, you see that we use this mu with a bar over it. This is wave number. And it is in centimeters, more specifically inverse centimeters, right? Centimeters to the -1, inverse centimeters. That's how you say it. But you can just call it wave numbers and we'll know what you mean. Just be careful because this formula here, whenever you're looking at C, C is in the units of meters per second. So here, the wavelength is in centimeters. So if you ever do a conversion, you have to make sure your units are agreeing. But here, if you look at the x-axis, it says wave numbers, and it says right there inverse centimeters. So here we're talking specifically about wave numbers. Fortunately, it has the same relationship. Low wave number, low energy. High wave number, high energy, right? So 400 is the low energy right here, and the 4000 is the high energy right there. Okay? This is pretty intuitive, right? Small number, small energy, big number, big energy. You want big wave number energy, small wave number energy. Okay? So far, so good? And so again, that's all this last bullet point is saying. It's saying that generally our IR spectrum, our IR spectra, all of them will be from 4000 wave numbers to 400 wave numbers. Any questions about that? Okay, moving on to the next slide. So again, why do we use IR? Because the bonds have the same frequency. That's really it. If the bonds did not vibrate with IR, we wouldn't use it. Very simple. However, one of your questions from the IR pre-lab quiz was, all molecules are IR active, true or false? And the answer is false, because while it is true that all molecules have bonds and all of their bonds vibrate, that doesn't mean that we can detect a signal, because ultimately we're using an instrument, we're using a detector. So how does the detector pick up the IR spectrum? Well, first of all, there's two conditions that have to be met. The first condition is the bond itself has to be polar. In other words, two different atoms, not the same one. If it has O2 is not polar. It's oxygen and oxygen. There's no dipole, right? N2 is not polar. Cl2 is not polar. F2 is not polar. Carbon-carbon bonds are not polar. They're the same atom. Make sense? It has to be different atoms. There has to be a polarity difference, like carbon-oxygen, carbon-nitrogen, oxygen-hydrogen, fluorine-hydrogen. Hopefully it makes sense. We call that different nucleus heteronuclear bonds. Heteronuclear bonds are polar bonds, and polar bonds have a change when you put them into a spring, right? You're changing the size of the dipole if you bring them closer or further apart. So you have to have a change in the dipole in a heteronuclear bond in order to have an IR signal. But that's only the first condition. The second condition is it cannot be symmetric. If you have a molecule like carbon dioxide, right? Central carbon, two oxygens. Let me give you the quick example over here. If we have carbon dioxide, well, the dipole goes in this direction and the dipole goes in this direction. They cancel out. So even though it is a heteronuclear bonded molecule, right? Carbon and oxygen are different atoms, and they will stretch, so it should cause a difference in polarity. Carbon dioxide, or at least this stretch of carbon dioxide, is not going to be picked up because it's symmetrical. Does that make sense? I'll explain a little bit more soon. But again, two conditions. You need to have a polar bond, and it needs to be asymmetrical to be picked up by the IR spectrum. And so you can see down here that OH is more polar than NH, NH is more polar than CH, and so the wave number of OH is going to be bigger than the wave number of NH, which is going to be bigger than the wave number of CH. Does that make sense? So any questions about this before I move on to the next slide? So just a quick recap. Molecules can absorb energy. That energy becomes a vibration. If the molecule is made out of two different atoms and it vibrates asymmetrically, you can pick that up with an IR detector. That's basically all we've said so far. Okay, I'm going to move on to the next slide. All right, so remember last week I showed you guys the different types of vibrations and all that other stuff. So I'm gonna show you before we do our practice examples. I'm gonna show you an actual 3D model of these vibrations. So this is just a 2D way of seeing it. So again, we have symmetric stretching. You know, you're kind of like a cheerleader with the pom poms, right? And just like that, you could also do like, go team, go team. Like you can do like one inside and the other one is coming out. We call that the asymmetric stretching. We can do them together, like go team, go, like bring them together. It's kind of hard to get in the right camera angle. And we can, out of the plane, like one is going forward, one is going backwards, like, kind of like that. Um, and it depends, right? This is only with three atoms. The more bonds you have, the more possible vibrations, right? So something like carbon dioxide is just like you can predict all the vibrations. Something like H2O, but something huge like a vanillin molecule, like an acetaminophen molecule, like that has a lot of vibrations. And so simple molecules have a simpler spectra. You see a lot less peaks. More complicated molecules have a lot of lines and peaks. So what we're learning to do is how to identify very specific stretches, very specific bends of the functional groups, right? You're going to see a lot of information, but you only need maybe two or three peaks. And so if you look down at the bottom, you see that example that I gave you earlier where carbon dioxide, the symmetric stretch, it does not cause a change in the dipole, so you do not see it in IR. But that same asymmetric stretch where one is kind of like in closer and the other one is further away, that one is asymmetric, so that one is going to show up and it's going to show up at 2350 wave numbers. Make sense? So again, we're gonna see this before I give you some actual examples of the spectra. So we're here to learn, okay? So I don't expect you guys to just get this in 1 hour and be like, wow, it's in my brain. I know everything. We're literally learning this, okay? So just bear with it. You'll see the patterns. This is just the theory behind it right now. So any questions about this so far before I move on? Okay. And we cannot drive home the point enough that we can think of this like a spring with masses, right? This is just the physics background justification for it. You see we have what's called the reduced mass. That's just the molar masses of the atoms. So you could actually calculate with higher physics and computer programs what the wave numbers of these vibrations should be. But that's for upper division courses. We don't really need to do that. We're not going to ask you to do that, but we're just trying to give you more foundation, more basis for this whole thing right here. And so again, the spring is a bond. So if you see those garage springs or those giant springs in your suspension system in your car, those take a lot of force to compress. That's why we put them on cars. Your whole car is like 4,000 pounds, and then you're going on the freeway. Those springs are compressing. You can feel the springs. You can feel it when you hit the pothole, right? Imagine how much energy it takes to bend that spring at all. Like it takes a lot of energy. Well, compare that to a weaker spring. Well, a weaker spring, you could probably just use your own hands. Heck, you could probably do it with like the springs in the pen, right? How weak are those? You can literally click them open and close. So some bonds are stronger than others. That's what I'm trying to get at. Some bonds are stronger than others. What are the strong bonds? Well, triple bonds are pretty strong. Carbon double bond oxygens are pretty strong. Carbon nitrogen triple bonds are pretty strong, right? They're shorter, so they're stronger. Single bonds tend to be the weaker bonds, right? So in the order you can see here in the blue bullet, triple bonds are stronger than double bonds are stronger than single bonds. And of course, that's not the only factor, the masses, right? If you have a giant atom next to a little one, the big one's not going to move that much and the little one's going to move a lot. But if they're the same size, they're going to move pretty symmetrically. They might not even emit a signal. You see what I mean? So you do have to think about these things. But we'll get to that once we practice a little more. This is, again, just the theoretical background. Any questions so far? Is all of this making sense? Like, you guys are okay with where we are? Okay. Moving on to the next slide. All right. Before I do this, I am gonna go ahead. Oh, wait, I think there's a question in the chat. Yep. Okay, everything is good. Thank you. Alrighty. Yeah. I'm gonna share a website where you can see 3D models of the vibrations. So give me a quick second while I find that. It should be, let's see. Hold on, I gotta first let me stop sharing. Give me 1 quick minute, please. Right there. Okay, I found it. So sharing my screen, going to this website. Alrighty. So this is called ChemTube 3D. Can everybody see it? Everything's good? You should be able to see a molecule of water, and it says up here ChemTube 3D. Really cool website. I highly encourage you to come and play with it after you're done. You can go here where it says structure and bonding, molecular vibrations IR. I clicked on water. I got to this page right here. So you see here a 3D water molecule. I can drag it around up, down, left, and right, right? Some people call it Mickey Mouse ears, whatever. And you see here is a diagram showing the direction of all of its stretches. You see it has wave number 1, wave number 2, wave number 2, but the wave number 2 here is a bend. So there's two types of motions. You have like stretching and you have like bending, right? Like somebody's pulling your arm versus pushing your arm to the side. It's different. And so let's go ahead and see how water moves. It says here, click to show the vibrations. You see we have 3 vibrations. The first one happens at 1711, and it's this one. We call this the bend right here, the one at the bottom. This is the bend. And you see that the bonds are bending towards each other, and that is causing a vibration to occur at 1711 wave numbers, or inverse centimeters, same thing, right? And you can see it's going in that specific direction. So then when a photon of that amount of energy hits a water molecule, the water molecule moves just like this. And since it gets absorbed, the percent transmittance goes down. That's why you see a peak in the IR spectrum. So those peaks are specifically the peaks of the vibrations. Make sense? So let's look at the other one. Look at this. This one is at 1711, but the other two are at 37 and 38. That's a big difference in energy. Well, that's because this one is a bend. Stretching vibrations require more energy. Again, think of the spring in your suspension system in your car. It takes a lot of energy to vibrate molecules that are polar and are strongly bonded, like an OH bond. Very polar bond, very strong bond, right? So here's one of those stretches. This is the symmetric stretch. You see both of them are symmetrically going into the oxygen and away from the oxygen. And there is another stretch called the asymmetric stretch, and you can see that one's coming in and one's coming out. Right? And so this is what we look for in the IR spectra. We look for the OH stretch at 3,500, at 3,800. And when we see it, we're like, hey, that peak specifically is an OH stretch because it's a highly polar bond that vibrates roughly at 3,800 wave numbers. And then we have a question. Individuals from the module, it was mentioned that water will make peaks, but water is symmetrical. Yes, so water is symmetrical, but it's the symmetry of the stretches, right? So you see the symmetric stretch right here? The symmetric stretch is probably lower intensity. However, while it is symmetrical, it's not exactly canceling out, right? If you look at the vectors and you add them together, you get a third vector. The vectors don't cancel out. So it has to be a symmetrical stretch in such a way that the dipole vectors cancel each other out. I hope that makes sense. And it's possible for one molecule to have one stretch that is symmetrical, but another stretch that is asymmetric. And so that asymmetric stretch does show up as a signal. Yes, so it will still fit both conditions in the end, right? The stretch itself has to cancel out. I mean, we're trying to make it simple by saying, arrows and stuff, but this is really like two vector matrices canceling each other out. Like you take like the vector sum of two dipole moments and they give you the zero vector. That's like linear algebra stuff. We're trying to simplify it by simply showing you the motions and the arrows and the directions. So does this make sense? Like, are we good? Any more questions about this one? I'm going to show you a more complicated molecule now. Let's do ammonia, NH3. So H2O, NH3, I'm adding one more hydrogen bond. And like I said, as you add more bonds, you have more vibrations, right? I think that's another question. Yes. Oh, yes. You're welcome. So click to show the vibration frequency list. Look at that. Water only had 3. Now we have 1, 2, 3, 4, 5, 6 vibrations. Just by adding one more hydrogen-nitrogen bond, we now have 6 vibrations. So the point is, once you have a lot more bonds, bigger molecules, you get a whole bunch of vibrations, you get a whole bunch of peaks. So again, let's start with the higher ones now. Look at this. This is a half symmetric, no, this is an asymmetric NH stretch along one axis only. You see that? It looks like a duck walking or something. Yeah. So this is one of the stretches. This one happens at 3565. A very similar one, 3565. Another one over here. This one is a symmetric stretch. You see that? Oh, that looks nice. I wish someone did that to my back. Just like, stretch out in all directions like that. That would be nice. But you can see this is a symmetric stretch, but notice how since the molecule is trigonal planar, all of the vectors still don't cancel out. They're not along the same plane. So they just add up in the bottom direction. You still have a dipole. So you still see this frequency in IR. And so notice that suddenly it drops down to the 1700s and the 1100s. Well, these are more bending, you see? The bonds themselves are not being stretched, they're simply being bent, right? So this one's like the other bend from water, like they're getting closer, like the pom-poms. And then what's the lowest energy one? This one. Yeah, look at this one. It looks like it's just like happy. It's like, oh boy, like your chihuahua when you get home from school. You're just like, hey, like this one is at 1132. And this is just by adding one more, we get a lot more vibration. So again, CHEM223A, you're very free to use it on your free time. You get a whole bunch of stuff. I've been using this throughout my entire degree. I still use it to this day. Let's look at one more. I want to look at a complicated one. Let's see. I think I saw vanillin earlier. Let's see, structure and bonding, molecular vibrations. Vanillin, that's right. We'll be using vanillin pretty soon. I think it's lab 5 or lab 6. So let's take a look at this right now. Look at that. A lot more complicated molecule, right? I see 3 functional groups. I see an OH on the top left. I see an ether, just the oxygen right there, the bridge. And I see a carbonyl, which is a carbon double bond oxygen. So I see 3 functional groups here. Those functional groups are going to have very specific vibrations only to those functional groups. So let's go ahead and check them out. And again, more atoms, more bonds, so we should see a longer list of vibrations, right? Let's see if we're right. Yeah, look at that. So these are all the possible vibrations from a molecule of vanillin, because it has a lot more bonds, so it has a lot more ways of moving, right? That makes some sense. Okay, let's look at the highest vibration only. Look at that. Make sure you look at this, because this is interesting, right? We have an entire molecule of vanillin, but only the OH is vibrating. You see that? Now think about it. O and H, it's a very polar bond. C and O is a polar bond, but carbon weighs 12 and oxygen weighs 16. They're very close together in mass, remember? It's a spring with 2 masses. And so oxygen weighs 16 and hydrogen only weighs 1. So it is a very polar, heavily size different bond. And you see the size of the arrow, that's huge, right? So it takes a lot of energy to vibrate it, but when it vibrates, it's very intense. Does that make sense? And only this molecule can vibrate at only this frequency because that's how much energy it takes to vibrate an OH bond. Just like you can only buy a $2,000 PC if you only have $2,000, right? You need that exact amount to vibrate the molecule. You need that exact amount of money to buy the item that it is that you're trying to buy. So I want to emphasize this to you because this is how we know what functional groups are vibrating, because we know exactly where they vibrate. Alcohols vibrate somewhere at around 35 to 3700. And we can see that. Let's look at the next one. Let's see, 3262. That one is a CHSP2 vibration. A double bond is stronger than a single bond, right? Remember, single bonds can rotate, double bonds cannot. So it's a lot more stiff. The spring is more stiff, so you need more energy to vibrate that. So that's why these are found at higher wave numbers. And notice that they're being stretched. All of these are stretching motions. So we call these SP2CH stretch. That's what we say. Let's look at the next one. That's another SP2CH stretch. You see that? Because that carbon right there is an SP2 carbon, and that H is vibrating. But it's only that one. Why? Well, it's between 2 carbon-oxygen bonds, so maybe there's something up with the polarity there. Let's look at the next one. This is a CH3 stretch. Look at that. Only the methyl group is vibrating. only at this frequency, nothing else, because everything else requires its own energy to vibrate. Does that make sense? Let's look at the next one. I think at 1699 we should have, oh yeah, that's interesting. See, all of them are vibrating in this way. So I mean, I don't know what we call this, but it doesn't look very intense. Look at the arrows. The yellow arrows are very small. So this would probably be like really small peaks that you could barely see. Let's look at the next one. I'm trying to find a specific one. Nope, that's not it. That's not it either. That's not it either. Hmm. I don't think they included it in here. Yeah. Let's go back and see the 1848. There we go. That's the one I'm looking for. Look at this one. This is the one that you're gonna see the most frequently. This carbon double bonded oxygen is called a carbonyl. I'll get to that when we get to that slide. The carbonyls are very iconic, right? I'm sure you know who Bugs Bunny is. I'm sure you know who SpongeBob is. I'm sure you know who Gandhi is. I'm sure you know, like, there's certain things that are just like iconic in their own field and culture. And the carbonyl stretch is iconic in IR. You like if you learn nothing else, at least learn the carbonyl because otherwise, how can you claim you know IR at all? The carbonyl is very specific. It always happens in the 1700s to 1850s, depending on what it looks like. And this is an actual picture of that. It's a carbon double bond oxygen vibrating. It's a very strong bond. It's a double bond. It's a polar bond. So it's very, very strongly vibrated when it gets activated. And of course, let's look at the smallest one, 71. Look at that. It's like a bending out of the plane. Look at that. It's like nah, mm-mm, right? So that's just a bend. Doesn't take a lot of energy. It only takes 71 wave numbers. So we're not even gonna probably pick that up. Remember, our spectrum only goes down to 400. So any questions about this? Any questions about the vibrations of the molecules, man? So next time you see your stoner friend, tell them, I'm sorry, you were right. The molecules are vibrating, man. I do want to show you benzene real quick, just for fun. Because benzene is a very symmetrical molecule, right? Look at that. But it still has vibrations. And look at this one. It's vibrating in the same direction always. I think this one wouldn't be active. This one definitely cancels out. This one, see, it's asymmetric, so this one wouldn't cancel out entirely. This one is not even a stretch anymore. Well, it's kind of a stretch in the CC, but it's more of a bend in the CH bonds. You see that? So again, I encourage you to come over to this website and just spend some time here and take a look at all of the vibrations of all sorts of molecules. I think you'll get the hang of it. There is one other website as well that you can look at. It's not as interesting, I think. It's from Purdue, right? Let me see. Do I have it on here? I don't think I do. No, I didn't. I was reading the dissertation of Paul Dirac. He was the first one to write about quantum physics. I'll link the website on the announcement. I personally think this one is a lot better. It gives you the information that you need. But if you are interested, you can Google IR vibrations Purdue, and you will get a website where you can also see all sorts of animations for the vibrations here. All right. So are there any questions before I go back to the presentation while I am here in ChemTube? Okay, I'm gonna go back to the presentation. Right here. Okay, so now that you've seen the actual motions of the molecules, hopefully these peaks mean something to you, right? So remember that alcohol that I showed you, the OH stretching very strongly? I'll tell you as a preview that this right here, this entire thing, this is an OH that is stretching. And look at the wave number. This wave number is 3400 roughly, right? High wave number, so high energy, and you saw in the animation that the arrow was very, very long. It was a very intense stretch, and that's why you see it go all the way to the bottom. It's at like 10% transmittance. And similarly, you start to see, oh, look, there's also these peaks. There's this one, 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 right? There's all sorts of peaks at very specific wave numbers. So they're fingerprints, right? We look at, first of all, what is the actual wave number? I told you the oxygen is at 34. This one here looks like it's at 15, right? Roughly 1500 wave numbers. This one looks like it's like 1050, maybe 1050. So first thing we look at is the wave number. Where on the x-axis is it located? We look at the shape. We have words to describe these peaks, right? So I'm going to ask you guys. I'm going to clear the drawings first. Somebody, please unmute your mic and give me an answer. How would you describe this peak? How would you describe it? Would you describe it as weak, strong, medium, narrow, sharp, blunt, wide, broad? What words would you use to describe that peak to somebody else? Okay, so Brandon said broad. Good, right? That seems like a pretty broad peak. It's not very sharp, so up it would be broad. Is it strong? Is it weak? Yeah, strong, broad, right? Strong, broad peak. This is how we talk about the peaks. We use these words to describe the shape of the peak. Strong, broad, weak, medium, strong, weak, medium, weak, right? We call that intensity. If it's strong, if it's weak, we call it, broad or narrow, depending on the range of the wave numbers. Yep, you guys are right on the chat. So we look at the shape and we look at the intensity. Is it all the way at 0%? That's very strong. That's like, I mean, it's strong because it has a high transmittance, as I'm sorry, a high absorption, a low transmittance, right? So you need to be able to look at this. When you're looking at a spectra, keep these three things in mind. This is what you're looking for. Any questions about this? All right. And like I mentioned, if you don't know your functional groups yet, you got to catch up because we're going to be using, like, if you don't know what the functional groups are, you can't even answer the questions here. You need to know your functional groups by name. You need to know the compound functional groups, meaning like a carboxylic acid, because you're going to see multiple peaks and you have to be able to put together the information, right? Okay, here we go. So this is the answer. This is the secret all along. Like I mentioned, they're very specific. So we know exactly where to expect them. You can see that we have this region. Depends who you ask. Make sure you check with your professor. Depends who you ask. I was told that 1000 and below was fingerprint region. Here it says 1400 and below is fingerprint region. I disagree with that. Some chemists will say 1200. Some of them say that the fingerprint region is useful. The point is, this is where the single bonds are. And we don't really look at this right away. This is kind of like the last thing we look at. Like, okay, we really can't figure out what else is in here. Let's look at the single bonds. But you're also not going into this blindly. Remember, you cannot determine the identity of a whole molecule based on the spectrum. So you kind of have some idea of where you're going. So you kind of only look at this if you have nothing else to go off of, if you kind of be like, okay, well, by the way, this further confirms my other hypothesis. Notice that the polar bonds are the strongest. They are at the highest wave numbers. Look, you have NH, you have OH, you have CH, right? The triple bonds, you have CC, CN. Those are at like 23, 24. The double bonds, like 1860, 1800. And all double bonds, right? Carbon, 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 oxygen, carbon, nitrogen. They're all next to each other on the periodic table. They only go up by 1 atomic gram every time, right? So they should be similar in terms of weight and stretching and polarities. And so again, we don't just go into this blindly. We know where to find them. So all we have to do is look at their shapes. Any questions so far? Okay. I'm going to go ahead and move on to the next page. All right, so let's start with zero functional groups. Just a plain old boring carbon chain. Nothing else. Well, since there's no functional groups, there are no vibrations of anything except what? What is the only bond that is vibrating? If all you have is an alkane, what is the only type of bond you have? I think somebody said it in the chat. CH, exactly. CH bond. Everybody agree? Because an alkane is just a hydrocarbon. Carbon-hydrogen. There's also carbon-carbon, but symmetrical, right? No polarity change, right? So carbon-hydrogen is the only bond that you can really see in an alkane, in an alkene, or in an alkyne. Alkene is the double bond, alkyne is the triple bond. So if you look at the bottom, you see the differences in all three of them. They each have their own unique signal depending on what type of bond they are. Triple bonds are shorter, so they're stronger, so they would have a higher wave number, right? So triple bonds have a higher wave number than double bonds. Double bonds have a higher wave number than single bonds. And sure enough, you see here at the bottom, let me get my pen. Here we go. So you see right there, you have a CH at around 3,300. So this is at around 3,300 wave numbers, inverse centimeters. This one is at around 31, maybe 3050 in this one right there. And over here, the whole thing is like between 2,800 and 3,000, right? So 2,800 to 3,000. So far, so good? And it makes sense because triple bonds are stronger, so their wave number is bigger. And so you see it has a weak, sharp peak if it is a triple bond and if it is a double bond. Weak, sharp peak. But sp3 CHs from a metal, that has, it looks like have you guys ever seen a picture of a cave? It has like the stalagmites. That's what I like to call them. That is always going to be there because in organic chemistry, we study the chemistry of carbon, and carbon will always want to make four bonds. And if there's nothing else, it will bond with hydrogen. So all organic molecules have CH bonds. So you will always see this shape in IR spectra of organic molecules. If you see nothing else except this, you know that you have an alkane, an alkene, or an alkyne. If you see other signals, you have more. This is like as simple and as clean as the spectrum is going to look like. Does that make sense? If you want to think about it in terms of hybridization, the closer you are to S, this has a higher wave number. The closer you get to P, you have a lower wave number, less energy, lower wave number. And that makes sense, right? S and P, strong, sp3, weak. The more P's you add, the weaker the bond. Any questions so far? I think we have a few questions here. Let's see. Why do these show if they're not polar? They are polar. Carbon and hydrogen do not have the same electronegativity. So even though in Gen Chem they tell you that they don't consider it a polar bond, the fact of the matter is there is still an electronegativity difference and there is still a measurable change in the dipole. So unless they're exactly the same electronegativity or exactly the same atom, as long as there's a change in the dipole vectors that is not symmetrical, then you will be able to observe the signal. Any more questions? These are good questions. Okay, I'm going to clear the drawings and I'm going to move on to the next one. Here's an example. Octane, right? Your gasoline, high octane gasoline. It's just hydrogens and carbons. So all you're going to see are the sp3 CH3 stretching, and you're going to see the sp3 CH2 stretching. And that's going to look like the stalagmites of the cave, and that's always going to be found between 28 and 3,000. This is always here. All spectra have this. You need to know what it is. You need to be able to tell me what it is. But since it's everywhere, knowing it doesn't give you any points because it's everywhere. You're going to see it everywhere. You need to be able to tell it apart from other ones. So yeah, once you know that what it is, that's great. But that's like being able to say, I can count to 1. Look, 1. Well, that's cool. All the other numbers are built off of 1, right? So all of the rest of the analysis is based off of what's different from this CH bonding, CH stretching. Make sense? And over here, you'll notice once again that our stretching frequencies are higher wave numbers than our bending frequencies. So stretching is higher than bending. You should know that. I will ask you something like that. Stretching frequencies are higher energy or higher wave numbers than bending energies. Any questions? Okay, let's move on to the next one. What happens when the CH or the CC bonds are aromatic? Well, remember that double bonds tend to be stronger than single bonds. So you're going to see higher wave numbers and you're going to see maybe different intensities. So here we have toluene. This is paint stripper. You can buy it at Home Depot, throw it on your walls, all of the paint will come off, right? Put nitric acid in it. Now you have nitrotoluene. Do it 3 times, you have trinitrotoluene, TNT, right? Don't do that. Anyway, so this is still hydrocarbon, CH bonds, but now it's a little stronger because it's a double bond. So that means that the wave numbers are going to be a little bit different. So let's take a look. You have this really sharp peak at 3000 right there. A singular sharp peak at 3000. It is medium because it's about 50%. So I would call this medium sharp. Actually, very sharp, I would say. Medium, very sharp peak. And you can see from the x-axis, it is located at around 3000 wave numbers. That is specifically your hydrogen ring aromatic stretch right there. Make sense? And then here you see these combination bands. That's just, remember how I showed you in the simulation, you have all sorts of bendings and vibratings and everything. That's what you see there. So when you think you have a ring, when you think you have an aromatic ring, look for a pattern up here that looks like these little mountains, these little tiny, very, very weak hills up here. And then at around 1500, at around 1480, 1500 right here, you're going to see also a very sharp medium peak. And this corresponds to your carbon-carbon double bond aromatic stretch. And then over here in the fingerprint region, I mean, yeah, there's this one here, but again, that's below 1000. So we don't really look at that unless we need more confirmation. And so again, note, you're going to ask me, well, what about this? What is that? ¿Quién sabe? I have no idea. What's this? I don't know. What's this? I don't know. What's this? I don't know. And what's this? I have no idea. Why? Because we're only looking for very characteristic signals. There's a whole bunch of signals. I'm sure we could sit down and analyze this, but you need actual quantum mechanics, you need vibrational spectroscopy mathematics, you need vectors and a whole bunch of other nonsense. The organic chemist only wants to confirm if things are going in the right direction. If you're trying to synthesize a functional group and you don't see the signal, something went wrong, flat out. You don't need any more information than that, right? So we're only looking for very specific signals in very specific places. Here you can see that we look for the medium intensity, sharp peaks of medium intensity between 1450 and 1600s for alkenes, specifically aromatic alkenes. So again, you see no other signals, so it's very easy to kind of start heading in the right direction when you see signals or the lack of signals. Any questions about this one? Okay, I'm going to move on to the next slide. The carbonyl. The carbonyl. Okay, I want to take a little bit of time to tell you guys that organic chemistry is very specific. I'm sure you kind of gotten the hint of it by now. I tell you guys from the very beginning, be very specific with your words, because if you ever get the chance to listen to two organic chemists argue with each other, it's like they're speaking a whole nother language. You're like, how can you even talk like that? How can you possibly put words together in a sentence and still have it mean something? I feel that way even to this day. Like the way that organic chemists speak is just absolutely insane sometimes. But that is because we're very specific with our language. So we're talking about carbonyls. A carbonyl is just this. Carbon, double bond oxygen. This is a carbonyl. It's not a ketone. A ketone specifically has other groups attached to that carbonyl. It is not a carboxyl. No, a carboxyl is C double bond O, single bond O. A carbonyl is only the carbon double bond oxygen. So when we're talking about carbonyl functional groups, we're talking about what functional groups contain a carbon double bond oxygen. And the functional groups have their own names, but they all have carbonyls because they all have a carbon double bond oxygen. So here they are, the family of the carbonyls. They are all their own functional groups. You need to know when you're talking about carbonyls, you need to be specific, just like you have a first name and a last name. Like if we were back in the Spanish era of exploration, it was like, what is your name? It's like Juan Ponce de Leon, right? Or something like that. Or like, who are you? I am, if you watch The Lord of the Rings, I am Aragorn, son of Arathorn, right? They used to address each other like that. Well, when you're talking about a carbonyl, you need to tell me this is a carboxylic acid carbonyl. This is an aldehyde carbonyl. This is a ketone carbonyl, right? Think of the carbonyl like the last name. Like, who are you? My name is, Esther, Esther carbonyl, right? You need to be specific. They each have their own wave numbers because they each have their own polarities. So look at, for example, the carboxylic acid. Let me use the color yellow. No, let me use blue. I'll use blue. You have the dipole there. You have the dipole there. Very strong dipole. Carbon and oxygen is a very polar bond. You also have a double bond, and you have two of them. So you should have a high wave number. And yeah, look, you have 1780, 1710. I think this is the highest of them all so far. Look at an ester. Very similar, but there's no hydrogen at the end. You also have the dipole. You also have a strong carbonyl, a strong carbon-oxygen single bond. That one, you just call it a carbon-oxygen single bond. Look at the amide. You also have two dipoles, but one of them is nitrogen, a lot less weak than oxygen. So the dipole, the wave number is lower. You see that? 1630, 1690. Not as strong as a carboxylic acid, not as strong as an ester, because nitrogen, carbon nitrogen is a less polar bond than carbon oxygen. Look at the ketone. This is a ketone. By definition, the ketone has to have two R groups attached to it. If there are no two R groups attached to it, it is not a ketone, it is just a carbonyl. But a carbonyl cannot exist just like this. It has to be bonded. It's just again that part. Just like you call this your hand, right? You have like obviously the entire like I'm Eduardo, all of me is Eduardo, but this is like the hand of Eduardo, right? But this is the carbonyl of the ketone, the carbonyl of the aldehyde, the carbonyl of the ester. This is how we talk. This is how when somebody tells you, this is what it means because they will talk to you like this and you have to know what it means. And when you're talking to me about carbonyls, you have to be able to talk to me about it specifically because then I'm going to tell you which one, right? They each have their own wave number. And I do want to say also that these numbers are not absolute. They are not going to be exactly at 1690 or exactly at 1725 or exactly at 1800. These are just general regions. Some of them can be overlapping. Overall, however, the carbonyl is found in the 1700s, plus minus, I want to say 500. So 1750, not 500, I'm sorry, 50. That's why I was like, what the heck? Plus minus 50, right? So 1650, 1750. Some of them go up to 1800 sometimes, depending on the molecule, but it's always in the 1700s region. Always. Very strong peak. Very high absorbance, very low transmittance. You'll see it right now. But before I show you, any questions about the carbonyl? And again, this is very iconic. So like if you know nothing else from IR, you should at least tell me like, well, a carbonyl is a carbon double bond oxygen and you can find it at 1700. Just like you can say the mitochondria is the powerhouse of the cell. Yes, amide is supposed to be spelled with an E at the end. That's just the typo from the slide creators. Yes. It should be amide, of course. Any more questions? Alrighty, so let's take a look. So here's two carbonyl compounds. They both have different functional groups. They both have carbonyls, but they are both different functional groups, right? So go here to 1718. I'm gonna use the color green, very lime green. So right here, this is your carbonyl peak. Look at that intensity. The y-axis. Look at the intensity. Look at the y-axis. It's almost to zero. That's almost complete absorption. This is why it's iconic. It's always a very strong, I mean, that's not very sharp. I would just call that sharp. A very strong, sharp peak. Look at the bottom one, butyraldehyde. Well, it has an aldehyde group, but it also contains a carbonyl. Look at that, 1720. It's almost close to zero as well. It's not always going to be the closest to zero, but it's going to be very, very strong around 1700. That's what makes it very distinguishable. And also, I'm going to use the color magenta or pink. What is this over here? In the 3000s, you see the stalactites? What are those? What are these right here? They're everywhere. Remember, I told you when we were talking about alkanes, these are everywhere. They're going to be present in every spectrum that you see. What are these? I think somebody said it in the chat. CH. That's right. These are CH bonds. Remember, you can also unmute yourself and say it out loud, right? Sometimes it takes me a while to see the chat notification. But yes, these are the CH stretching bonds. So the CH stretching bonds are always around 3000, 2900, 2800. You should know that they're there. Most of the time, they don't tell you much of anything, right? So then the question becomes, well, look at that. One is at 1718, one is at 1720. How do you tell the difference between the two? Well, the aldehyde has this CH at the very tail end right here. You see that? Where do you find CHs? You find them between 3000 and 25, 26, 27, 28, right? So you see there's two signals here at 2720 and 2820. They're a little bit lower wave number than the rest. Right here, right here. Those are specifically this one right here. This is what we call an aldehyde CH stretch. Right there. Aldehyde CH stretch. That can help you tell the difference when you have a carbonyl peak and you want to know if you have an aldehyde. Sometimes it's one peak, sometimes it blends in and you can't really see it, so you need other information, right? And again, I'm going to change color now. I'm going to use red. You can be like, well, what about this? Well, what about this? And what's this? Who knows, man? Who knows? I'm not going in blind. I should have an idea of what I'm looking for. What is this over here? I don't know. Something? What is that? I don't know. Probably some bend of some part of the molecule. All I care is that I'm supposed to have a carbonyl, so I see the carbonyl, and I'm supposed to have a CH aldehyde stretch, and I see it right here. That's enough for me. So this is what I mean. You see all of this, and you might panic. You might be like, oh God, all these spectra, all these lines. Nah, you just need to look at very specific signals. All right? So any questions about any of this? Make sense so far? Okay. So we're gonna move on to the next slide. I'm gonna clear all the drawings again and then move on to the next slide. Alrighty. So carbonyls and double bonds can participate in an interesting effect. I don't know if you've talked about this in class yet or you've heard about it. This is called conjugation. Conjugation. Conjugation means alternating single double bonds. So I will draw you an example. If you have a double bond followed by a single bond, followed by a double bond, followed by a single bond, followed by a double bond, followed by a single bond, blah, 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 ad infinitum, right? Forever and ever. As long as you have that condition of alternating single double bonds, that is called a conjugated system. Conjugated system. We call it conjugation. And this can happen as long as it's a double bond and a single bond alternating. So you can also have it with a carbonyl, single bond, and then a double bond, single bond, and then like another carbonyl, and then another single bond, and then another double bond. Like this is also a conjugated system because you have alternating single and double bonds. Okay, so you need to know what a conjugated system is. Conjugated systems very likely have resonance. resonance structures, right? So when you have resonance, that means that it's not entirely a double bond and it's not entirely a single bond. It's like a 1.5, 1 1/3, 1 1/4 bond, depending on how many resonance structures you have. So any of those numbers is less than a double bond. So the wave number is going to weaken. The energy is going to be weaker, right? So as soon as you have anything lower than a double bond, it's going to have a lower wave number and lower energy to vibrate compared to a double bond. And also it's going to have higher energy than a single bond. It's in between. So this is why conjugation is important. If you look at the bottom example, a carbonyl of a ketone at 1720, as soon as you introduce this double bond and make it into a conjugated system, well, now this double bond of the carbonyl is now like a bond and a half because you have this resonance right over here. You see, like it would look like this. The charge is spread out. So you don't have a double bond anymore. You have a 1.5 bond. That's weaker. So the wave number is lower. You see that it goes down to 1680. So if you have a conjugated system, your wave number is also going to be going lower. This is why I'm telling you that you can have a ketone carbonyl, but depending on the rest of the system, it's not going to be exactly at 1715 every single time. So you have to take into context the whole molecule. Any questions? Okay, moving on to the next slide. Alcohols and phenols, finally. So alcohols and phenols. Phenols are just a benzene ring that have an alcohol attached to them. So just be aware they ultimately are just alcohols. So this is what a phenol would look like. That's a benzene ring, OH, and then maybe you have something up here, right? Either way, this still contains an OH group, right? So alcohols and phenols both have the hydroxyl group. You see that right here, the hydroxyl groups. Well, this one is a polar bond made out of a big atom and a small atom. So the spring is very, very like intense, but they can also hydrogen bond to each other. Remember, hydrogen bonding is where you have OH, NH, or FH, and that can bond to an O, an N, or an F by hydrogen bonding. I'm just going to draw like this to emphasize hydrogen bonding. They're not actually bonded. It's hydrogen. It's like a magnetic sort of bond, not really electron based. And so that just creates more restrictions. That just creates a stiffer spring. So that means the wave number is higher. And that's why you find those bonds up in the highest wave numbers, 35, 36, 37. And so you see down here in the example of hexanol, I'm going to use the color, let's use pink again. You see, it's a very broad signal, right? This was actually the very first one that we saw. I told you guys this is an OH. So this is a broad, strong signal that starts at around 3200 and it ends at around 3500. So 3200 wave numbers to 3500 wave numbers, right? Or inverse centimeters. You can say either one. And so OH, it always looks like this. Like, of course, there's exceptions, but you're always going to find it in that region. It's always going to be strong and it's always going to be broad, right? Why is it broad? Because some of the OHs are hydrogen bonded, some of them are not. There's a distribution, a statistical distribution of how many oxygen hydroxyl groups are bonded to each other via hydrogen bonding. And so you see the signal looks like a Gaussian distribution because some of them are, some of them are not. And so you just see the signal spread out throughout a large range. That's why OH is characteristic. That's why you can identify it very easily. What is this right next to the OH? I'm going to use the color ice blue. What is this right here? At 3000. What is that in the blue? CH bonds, exactly, right? And it says here that it's hexanol, so you know that it is sp3ch stretches, right? sp3ch stretches. And that's always going to be in all of your spectrum because organic chemistry's definition. And that's really all we look at. What about this right here? Oh, well, what's that? I don't know. That could be some sort of bend, some sort of stretch. not really important. It's at 1500. A lot of things are at 1500. We can't really say what it is. I'm sure there's something, but I mean, if we know that it's hexanol, all we know is that we have one OH and six carbon hydrogens. So um, we don't really need that information. And then, of course, even though you have the OH, don't forget that you also have C and then O and then H. This carbon-oxygen bond is polar, but it's a single bond, so it's weak. So you're going to see that at around 1100 right there. So at around 1100, you're going to see your carbon-oxygen single bonds from ethers, from esters, from carbon-oxygen hydroxyl groups. You're usually going to see that around 1100. Any questions so far? We okay? Okay, I'm going to clear the drawings. Moving on to the next example. Oh, I think I skipped too much. Nope, there it is. Alrighty. Wait, let me check the chat. All good. Awesome. Thank you. Alrighty. And so over here, carboxylic acids. Well, a carboxylic acid contains two subfunctional groups, right? It contains a carbonyl and it contains a hydroxyl, right? Carbonyl plus hydroxyl, COOH. That is a carboxylic acid. So when you're looking at the IR spectra of a carboxylic acid, you have to look for both of those signals. So the OH, once again, OH is very broad, right? But look at the first difference. Right here, it's even broader because now you have two potential hydrogen bonds, right? This is an H bond. Here's another H bond. You have more H bonding, so you have a wider distribution. So carboxylic acids usually start at 2500 and they go to 3500. So you can find those from 2500 all the way to 3500. And we call this the wizard's beard because some people have said that it kind of looks like, I'm really bad at art. So like if we just draw the eyes of a wizard and this is like the wizard smiling and here's like the wizard hat, right? You could see this right here would be like the beard of the wizard. So when you're looking for a carboxylic acid, look for the wizard's beard. That would be an indication, right? What is the beard? What is this at 3000? I've been asking you guys that for every single spectral. What's this here at 3000? What are those peaks at 3000? They're everywhere. Those are CH. That's right. Those are CH stretches. They are always going to be present. It just so happens that here, the broadness of the OH, of the hydroxyl from the carboxylic acid, happens to overlap with the same frequencies as those. So they blend together. That's what gives it that beard look. So if you see the wizard's beard, you have an OH that is most likely a carboxylic acid one. How do you confirm? Well, it's a carboxylic acid, so you also have a carbonyl. So look for your carbonyl peak. If you have a carbonyl peak and an OH peak, you must have a carboxylic acid, right? Make sense? So this is your carbonyl, roughly at around, it looks like it's at 710. I don't know exactly, but again, notice it's at 1700-ish, right there. Very strong peak. Make sense? So wizard's beard plus this will give you carboxylic acid. What was the other bond you needed to look for the wizard's beard? The carbonyl, the one that I just pointed to right here at 1700. So if you have the wizard's beard, you have to find the carbonyl. I'm not sure what you mean. What was the other bond you needed to look for? Because you need to look for two, right? If you have a carboxylic acid, you have to look for the hydroxyl and you have to look for the carbonyl. The wizard beard is an OH. Is that what you're asking? Yes. Okay. Yeah. Yeah. The wizard's beer is an alcohol, right? Remember, alcohols are very strong polar bonds, so they are found at a very, very high wave number. Alrighty. So let's take a look at some examples then. So, oh, no, before we look at some of the more examples, we have to look at the next one. Okay. So carrying on, we have carbon-oxygen bonds. There's different types of carbon-oxygen bonds. This one right here, dibutyl ether. So we have dibutyl, so we have 4 carbons, 1, 2, 3, 4, and it's an ether, so there's your oxygen, and it's dibutyl, so we put another butyl chain. So we have 1, 2, 3, 4. This is our molecule. The only functional group present is an ether. So again, look at the spectrum. Very simple. Not a lot of noise. What's this at 3000 over here? The CH bonds, right? Yep, you guys are getting it by now, right? This is always a CH bond over here. So that doesn't really tell us much. Of course, it's a hydrocarbon, right? So what's this at 1100? I just told you guys earlier that you can see that at 1100, you find the carbon-oxygen single bond. And you kind of expect that because it tells you right here on the spectra what the formula is. So this might be something I might give you on the post-lab quiz. I'll give you this IR spectrum. I'll give you the structural formula, and I'll have you tell me which functional groups are here and point to them, right? And you have to be able to know. What if you get confused and you're like, well, maybe this one is and this one is, right? Well, sure, but look at the intensity. This one is at like 70 and this one is at like 60-ish, right? That's not very intense. And a carbon-oxygen single bond is very strong, even when it's a single bond. So it's very intense. You still need a high intensity of energy to shake it. So carbon-oxygen bonds are always going to be intense. That's how you can tell which ones they are. Whether it's a carbonyl or a carbon-oxygen, they're going to be relatively intense. Make sense? Okay. Let's see what the next example is. Let's see. This is for esters. All right. So now we get another one, another type of carbonyls. So let's see. Drawing with the red. We have carbonyl, O, and then something over here, and then something over here, right? So this is like a carboxylic acid, but there's no hydrogen. It's simply just an ether bridge, right? Carbonyl and an ether. So you look for both signals. You look for the signals of the carbonyl, you look for the signals of the ether. So here, once again, at 1700, you have a very strong, highly intense peak. That is obviously your carbonyl right there. Almost always it's going to be your carbonyl. Look at around 1100. Well, not exactly at 1100, but a little bit further, you see that carbon-oxygen stretch right there. Notice how intense it is. It's also very strong. And so that basically gives you all the info you need. What's over here at 3000? You should know by now. What's this at 3000? It says right there. Just tell me because I need to drill this into your head. That is the CH bonds. That's right. You see? So I could do that with the carbonyl too, but not everything has a carbonyl. Look at the bottom number. The bottom number also is an ester, but it is an aromatic ester. So remember that aromatic rings add a little bit more twists, a little more interesting things to the spectrum. So let me use another color, green. Once again, for when you have an aromatic ring, you'll often see very sharp peaks. Instead of the stalagmites, their intensity decreases because remember now you have like an sp2 hybridized carbon. It's a lot stronger. So you see the intensity is a lot less. The peaks are also a lot sharper. Notice here at the bottom molecule, you still have this carbonyl right there, and you still have the same intensity. It doesn't really affect the carbonyls that much. You also have a few sharp peaks, a little bit lower than that, because carbon is lower than oxygen in terms of molecular weight. But you still see those. Those are typical of aromatic carbon-carbon double bonds. And again, you have this carbon-oxygen single bond from your esters. Actually, you have two. You have carbon-oxygen and then the carbon-carbon to the methyl group. So you should see two of them. And sure enough, look, there's one right there and there's one right there. So you see, what about the rest? For example, you might be like, well, look at this. This is also very strong. Why aren't you talking about that one? That's probably something with the carbon oxygen as well. And it's probably some sort of stretch, but it's probably a weird asymmetric, carbonyl methyl carbon oxygen bond. That's getting a little complicated, right? Just look for what's easy, look for what's expected, and then you can worry about the rest, right? So this one, who cares? This one, who cares? These here, who cares? What these, I mean, they might be significant. This one might be significant, right? But I mean, it's at 1,000. We haven't talked about anything at 1,000. So I think it's pretty safe to not really pay much attention to it, right? We go by process of elimination. We find what's easy, then we explore what else might help us. So does this make sense? Any questions so far about the analysis? Okay. So moving on to the next slide. Amines. These are interesting. Amines are polar bonds. So instead of NH, think of OH, right? NH, OH. Well, how many NHs? Because NH is a polar bond. And if you have two of them, you can see two signals. And so you see that primary amines, they have two NHs and one NC. That means you have two signals. Primary amines give you the two signals here on the left. Secondary amines give you one signal that you see here on the right. And notice that the stalagmites of the CH stretches are here. They are always higher wave number than the stalagmites. So if you see a weak, sharp peak to the left of the stalagmites and you're expecting an amine of some sort, you can find out exactly if it's NH or NH2 simply by actually counting how many peaks you observe. This is one of the few instances where the IR spectra can tell us something about the structure, but very rare. And of course, note that it says that a tertiary amine will not give you any peaks. And that is because these peaks are specifically nitrogen-hydrogen peaks. If you have a tertiary amine, these are nitrogen carbons. There is no NH, so why would there be a signal where NH is supposed to be? So only primary amines and only secondary amines are going to be here. Does that make sense? Any questions about this? Okay, moving on to the next one. All right, so now we get to the part where I ask you guys and you guys tell me via the chat or via voice what these are. We're down to 14 people. Some people have left. Not good. Well, I hope they're okay. Alrighty, but yes, remember we're here for usually 2 hours and 45 minutes. So if this was an otherwise normal day of class, we would still be in class. So unless you have to go, please let me know. Alrighty. So what functional groups are present here? Okay, I already have an answer. Make sure that if you're answering on the chat that you can message everybody, because if you message me directly, nobody else can see your answer. And Tanya said audio cut out. We're just trying to figure out what functional groups are present here now. So here we have a spectrum. We have no other info. Based on the spectrum, what do you think is present in the molecule? What is the functional groups that are present? And again, when you answer, please make sure you address everybody in the chat so everybody can see your answer. What functional groups are present? OH, broad, medium, strong, CO, strong, narrow. Be specific. CO what? Is it CO single bond, CO double bond, CO triple bond even? They exist. What kind of CO? CO double bond, right. That has a very specific name. What do we call it? Carbonyl. That's right. Remember, a carbon double bond oxygen is called carbonyl. So be very specific with your words. So yes, we have the carbonyl right here at 1700-ish. And then we have the wizard's beard. I hope you can see the wizard's beard, right? There's your wizard and there's his beard. Very happy guy, right? And I guess Santa would be better actually, since Christmas is coming. And then of course you have your CH stretches right there at 3,000, right? This bottom part of the beard right there. So there's definitely a carboxylic acid in here, for sure. What else? Well, I don't know. Look at these weird peaks over here, right? What could that be? I don't know, man. What could that be? I don't know. Something. All we know is that we have enough evidence to say for sure we have a carboxylic acid. So we can kind of not pay much attention to the rest. Yep. Yep. So it's not maybe an OH stretch, it's definitely an OH stretch. So remember that when the OH is part of a carboxylic acid, it usually starts at 2500. You see, you can kind of begin at 2500 to 3500. You see? So this is like the really broad OH signal right there. So if you see that, if you see like a range of 1000 wave numbers, that's most likely the wizard's beard OH right there. Make sense? Okay. So next example. What functional groups are here? What is in this molecule? Secondary amine? Secondary amine, well, the secondary amine signal would be weak, right? And right there, the transmittance is 30. That means that it's a very strong signal. It's getting heavily absorbed. So based on the intensity, we can rule out a secondary amine. So what else could it be? An OH stretch. That's right. This is an OH stretch. Why? Because OH is a strong bond and it also has hydrogen bonding. So you can also see that it broadens out. This is an OH stretch. High wave number, right? Look, this is at 33, 32 to 35. Between 32 and 35. It's lower than 50, so I would call this strong. Medium is like 50, 40, 55. So this is definitely a strong broad peak right here. What's over here at 3000s? I think somebody already said it in the chat. Yep, sp3CH stretches. That's right. That's always present. Those are always very intense. That's why they're called the stalactites. And I don't know what else is in here, right? You can't really tell if there's anything else much in here. So somebody said, no, you can't just be guessing just willy-nilly. You have to give me evidence, right? So you said there's a carbonyl in here. Okay. Well, let me look at 1700. Right here is 1700. Is there any peak at 1700? Right? So it cannot be carbonyl. I'm glad you brought that up because that's actually something I see a lot, especially in the post-lab quiz. People just throw out carbonyl. They're just like, this is a carbonyl. And they're like Oprah, this is a carbonyl, and this is a carbonyl. Carbonyls are at 1700s. If you're not looking at anything in 1700s, you shouldn't even be thinking of carbonyls. All right? So again, we're here to learn. I hope you learn it because carbonyls are so iconic that it's hard to confuse them or miss them, I would think, once you get used to them. We've only learned IR in the past 2 hours, so I mean, I don't expect you to still know everything right off the bat, but it just gives you an idea of what to look for and what to practice over the next few weeks. So thank you, thank you. Uh, Anything else? Any other questions? Alrighty. So next example. I didn't clear the drawings. Here we go. Alrighty. So what are the functional groups in this molecule? The functional groups in this molecule. What do you guys see? Okay, there's an answer in the chat. Definitely OH and C double bond O this time. It's both at 3000 and 1700. All right. Well, let's check it out. Let's see. 15, 16. This is 1700 right here. Oh, my thing is not drawing out. Give me a second. Okay, here we go. So here's 1700, and even though it's close, it's not exactly at 1700. And remember that carbonyls are very strong. Like it's going to be very close or at least below 20% in strength, right? So carbonyls are specifically at 1700-ish and they're very strong, so this cannot be a carbonyl. So again, don't just be throwing out carbonyls because you're like, well, everything's a carbonyl now. It's not, right? Very common misstep, but let's try to focus specifically on an actual carbonyl. So you said OH. Well, remember OH is also a very strong one as well, right? We saw it earlier. It kind of looks like this, like a very smooth, broad signal. This signal here, you see it's actually a little less than 50%. So it's actually not strong at all. This is actually like weak medium, like it's medium but a little weak. And also it's not one peak. There's two peaks here. You see that? One and two. That's very telling. That's right. That's right. So Brandon said two peaks, primary amine, right? So it's an amine with one carbon bond, and then the other one is H and H. And these NHs are these peaks right here. Does that make sense? So let me clear the drawings real quick. And so once again, this is your NH. This is your NH. How can you tell the difference? They're weaker than an OH. And there's two of them. The OH is a single one. And the OH goes from around 3200 to 3500. Well, this one does as well. So I guess that's not very distinctive, right? But the OH would be like around here and it would be a lot broader. And it would only be a singular peak. And it makes sense, right? Because if you look at the periodic table, you have carbon, nitrogen, oxygen, fluorine, right? So OH and NH are pretty similar and they're right next to each other. So of course they would be in a similar region, right? And yes, he said NH2. That is right. Yes, it is an NH2 primary amine group. So yeah. And what's this over here at 3000? People are in the chat. Yep, CH, exactly. Those are CHs. Okay. And again, that's really all the info we need. You're gonna be like, well, what about this one here? What about this one here? Quién sabe, man. Like, I need more info. I need to see if the molecule's a ring or just a chain to kind of make some guesses. I can't just tell. But right away, right off the bat, I know I have an NH2 here somewhere. And maybe that's all I need. So we don't pay attention to every single peak. We only look at the characteristic peaks. Let's see. Someone else in the chat? Yep, CH. Alrighty. Okay, any more questions about this one? All right, moving on to the next slide. Yeah, what about here? Remember, we're looking at intensity, wave number, and shape. CH and NH. Oh, sorry, I've been switching. Okay, here we go. CH and NH. Again, I need you to be more specific because what is it? CH like sp2CH, SPCH, aromatic CH. Like, you need to be very specific when you're talking, right? What's your name? I'm human being. No, what human being are you, right? Secondary amine. That's right. That's right. There's only one NH here. And you can see again, it's not very strong. It's like at 50%. It's not very broad, right? It's kind of like a slimmer peak. If this was like an OH, it would kind of look more like this, I would say. A lot more wider, a lot more towards the bottom. But it's not. And oh wait, hold on. Clear all the drawings. Okay, I don't know if they're cleared or not. I'm kind of having a hard time with the drawing here. But anyway, so yeah, this is your NH right there. Oh, pues. Here you go. This is your NH right there. NH. And then there's one R. There's another R. What's this over here at 3000? Aromatic compound question mark? Well, if so, we would observe like a little series of bands up here And we would also observe like very sharp peaks around the 1500s, 1550s. These are a little lower than that. So, I mean, it might be possible. It's also hard to see since it would be obscured over here if it was an aromatic. Yeah, they are medium peaks, right? But honestly, we would need more information about the molecule. It is possible these are carbon-carbon double bonds. I suspected that earlier as well myself. But like I mentioned, without more information, it's impossible to tell. The only for sure thing we can tell from this spectrum, absolutely, is that we have an NH bond somewhere. Yeah, see, but you're still thinking correctly, right? You're not wrong. It is possible that's a carbon-carbon double bond. We need more information. That's really it. Any more questions about this one? Alrighty, moving on to the next slide. All right, unknown number one. Just more practice, right? What's in here? What are the functional groups here? OH bond. Does anybody agree, disagree? sp3ch, of course, that's always present most of the time, right? sp3ch is always present. All right. So yeah, this is definitely an alcohol. So I think Tanya, you were guessing alcohols earlier, right? Do you see how the alcohol peak looks different than the NH peak? You see how it's a lot stronger and a lot broader, and it's like it's almost more smooth. Somebody described it as blunt earlier, right? And so this is why, the more problems we do, the more you start saying like, oh yeah, of course that's this one, of course that's this one, right? So by now you should start seeing that, yeah, look, the OH is usually very smooth, it's broad, it's usually between like 3200 and 3500 only, right? A parabola. Yeah, actually, that's a good description. A parabola. And of course, here you have the stalactites, your CHSP3 stretching most likely. Um, there's no overbands that indicate an aromatic ring over here. There's a sharp peak right there, but I mean, that could also just be a band. We don't really know. We would need more info for these cases. It's not always at 20%, but it's definitely like lower than 40, like 30. Usually it's strong. You will definitely be able to tell. It's also just it looks like this, right? It looks like a parabola. Like it's very distinctive. It's hard to get it confused with something else once you start really seeing the examples. And at the end of the presentation, I'll show you where you can find examples so you can practice on your own. Yes. Alrighty. So any questions about this one? And again, sometimes we only get the information about one group and the rest of the stuff. That's why we do NMR. That's why we do TLC. That's why we do melting point analysis. This is just another piece in the puzzle, another way we can analyze compounds to further identify and confirm their identity, right? Imagine how they must have done it in the 1850s when there was no spectroscopy, no absorptions. Like they had to burn it and measure the quantity of air, and oh man, it was crazy. I don't even know how they managed to discover anything back then. But yeah, truly impressive that they were able to do it. And now we have instruments. All we have to do now is learn how to read squiggly lines. Lucky us. Alrighty. So I'm gonna move on to the next problem. Okay, this one here. What functional groups are present? What functional groups are present here? Just the CH. What makes you say that? Nothing else is on the graph. That's 100% right. Nothing else is on the graph. Does everybody agree? There is no carbonyl at 1700. There is no hydroxide between 32 and 35. There are no carbon oxygen single bonds at 1100 or 1200. You see that? There's nothing else but the CH peaks, and a few CH stretches. But there is more information here besides that. One of the first clues that I'm going to point to are these tiny little hills up here at around 1800. Very, very weak, but very telling as well. Right? You see these right here? There's like a little tiny amount of hills. And we call those the Oberbands. That usually comes up, as Nikki just said, in an aromatic compound. And also look at this very strong, sharp peak where you usually find your stalagmites. This is your aromatic hydrogen stretch. This is your, carbon, double bond, single bond, aromatic hydrogen stretch right there. Very distinctive. Also, this peak is very distinctive. What is that peak right there? And then Nikki asked, the little bumps don't have to be the same size. No. As long as you see something that looks like very weak little hills, and sometimes you don't see them either. It depends on the molecule. But if you see them and you see like a spectrum like this with a lot of sharp peaks, that tells you very likely aromatic. And then he up to this one said double bond. Well, be specific. Is it the carbon-carbon double bond, or what about the double bond? Be more specific. So this one right here would be a carbon, sp2 carbon, hydrogen stretch. And sp2 carbons usually have a double bond somewhere in there. So it's a carbon-hydrogen stretch of an sp2 carbon. The carbon double bond is this one right here. This is your carbon-carbon double bond. Notice it's not very strong in this example. And that's why I don't want to say that you're always going to see a strong transmittance or absorption of the carbon-carbon double bond. But since we know it's aromatic, we can reasonably deduce that this must be the carbon-carbon double bond stretch, right? It's close to 1700. Carbon and oxygen are next to each other in the periodic table, so this is where a carbonyl would roughly be, but it's not polar, so it's a lot weaker. That's why we see that. And this is probably some sort of other aromatic carbon-hydrogen or carbon-carbon bend, but we don't know for sure. All we care about is this one on the very left, the very sharp peak, and this one right here at 1700. And of course, the absence of other signals tells us this is just an aromatic alkene. Make sense? All right. So let's move on to the next example. What about this one here? CO. Again, you gotta be specific because is that C single bond O? Is that C double bond O? Is that C triple bond O? I mean, all of those are COs. Carbonyls. That's right. That's right. You have to call it what it is, right? A rose by any other name is still a rose, right? Yes, a carbonyl is a carbonyl. Where is the carbonyl? Give me the wave number. Give me the actual number. Where is it at? 1700, right? Yep. So 1700 is right here, a little bit to the left, right? Yeah, you could say 1700. You could say 1710. You could even say 1720, right? As long as you get the gist that it's at 1700, notice it's strong, right? Its transmittance is only about 25%. So that's a very strong absorption. That's a very, very strong absorption, very strong signal. So that's how we know it's a carbonyl. So if it's a carbonyl, what type of carbonyl? Is it a carboxylic acid carbonyl? Do we see the wizard's beard? No wizard's beard, right? So this is not a carboxylic acid carbonyl. Do we see a carbon-oxygen single bond of an ester? Well, if we did, we would see it at 1100, right? So let's see, 1100's right here. We see something there, but it's not very strong because look at the strength of the carbonyl signal. Remember, carbon-oxygen is a very strong bond, single or double. So the intensity will be high, even if the wave number is lower. So here, this one is weaker. I don't think this is a carbon oxygen. This is not a carbon oxygen single bond. So this is for sure not an ester. So what is it? What else could it be? Could it be an amide? Because this could this be like an NH or an NH2? No, because why? Why can this not be an amine? No NH bonds, no NH signals, right? There's nothing here that looks like that. Make sense? So this cannot be an amide. So what else could it be? We still haven't gotten our answer. It could be just a ketone, right? That's one possibility for sure. Since it doesn't seem to be anything else, we could just say it's a ketone. But there is a little hidden detail that you can use. I'll give you a clue. It's in the stalagmites. There's a very particular stalagmite that tells you what it is. What are the stalagmites? What are they usually? What kind of stretches are those? The stalactite stretches. What are those? What's at 3,000 usually? CH, right? Notice there's one specific peak right here that's lower than the rest. And yes, Nikki said, is this an aldehyde? Is this a CH? 100%. So this is actually an aldehyde carbonyl, right? If that wasn't there, if that looked like the rest of the stalactites, just otherwise normal and whatever, then yeah, you might just assume it's just a ketone. But that individual, like tiny one, tells you that it's an aldehyde. It's just practice, right? It might not be apparent right away because we just learned this like an hour ago. So again, if you're still like, well, I don't know, well, I mean, I'm still not sure, that's okay. You got to let it settle in your brain for a few days. That's why you get 2 weeks before the post-lab quiz, and that's why you get 2 weeks to complete your assignment. So, just relax and take it as it comes, right? All righty. Any questions about this one? All right. What about this one here? And I'm gonna give you guys 2 minutes real quick. I think my dog is like wanting something. So think about it for 2 minutes. I will be right back real quick. So give me a quick second. So think about it. What do you see here? All righty. All right. Sorry about that. I think she needs to go out, but we're almost done. All righty. So what did we come up with? What's here? You had a little bit of time to think about it, so you should have an answer by now. sp3ch for sure, right? Because what else is here? What else is here? There's no carbonyls, there's no amines, there's no alcohols, there's nothing else. This must be just a plain old boring alkane, right? Just this regular CH. Make sense? There's nothing here. All right. So any questions about this one? This one's pretty easy, right? So sometimes the absence of signals is also enough information. All right, next example. What about this one? Alkane is single bond and alkene is double bond. Yes. Ane is a single bond. Ene has at least one double bond. All right, sp3ch primary amine. Okay, so yeah, we have the sp3ch as always, and we have a primary amine because you see the two weak peaks right there. Let me go ahead and get the drawing again. Here we have 1 and 2. These are your NH stretches right there. And there's two of them, so it must be 1, 2, NH, NH, and this must be some carbon. And there's nothing else. So this is your regular sp3ch stretches. There's nothing else, so that's all the information we can get. This is just an NH2 in there somewhere. Any questions about this one? All right, moving on to the next one. Now, before you begin looking at this one, I do want to say, look at the transmittance on the entire spectra here. You see that the baseline is roughly at 60% or so, right? Sometimes when you run your instrument, you get spectra that looks like this. It looks a little funky. The transmittance is not at 100% the lowest one, the baseline, right? Uh, you can still see some information. This is the equivalent of having a TLC plate with excessively big spots. But if that was the case with you guys, you remember I told you we can still look at it and get some information out of it. This is true for a spectrum that does not look very well calibrated. You could still get some information out of there, but this is where you got to count on your pattern recognition. So, what if you have to guess, what do you think is in this spectrum right here? All right. So Brandon said carbonyl, Jaden said carboxylic acid. So which is it? It's both, right? Because a carboxylic acid contains a carbonyl and a hydroxyl. So it's both. But you can't just tell me carboxylic acid because carboxylic acid is both of them. You have to tell me what signal is which. So let's go ahead and start with this one here. It goes from 25 to 3500 wave numbers. So what is that? What is this one right here? OH, that's right. This is the hydroxyl or the alcohol, if you want to call it that. This is the OH. And this is the carbonyl. See, double bond O? Look, exactly at roughly 1700, right? So when you have a really broad signal that looks like a wizard's beard between 2500 and 3500 plus a carbonyl peak, well, look, carbonyl plus hydroxyl equals carboxylic acid, right? So, but again, you can't point to this signal and tell me, oh, carboxylic acid. You're partially correct. Which of the two? You have to be specific, right? This is the hydroxyl of the carboxylic acid. This is the carbonyl of the carboxylic acid. Any questions about this one? All right. Okay, moving on to the next one. All right, and I believe, I'm not quite sure, I will confirm with you guys, but I believe that you're gonna get some sort of table like this for your exams. I'm definitely gonna give you a worksheet, a little graphic where you guys can reference it during your post-lab quiz. I mean, it would be nice to know in general where things are, but you're just learning it. So if you memorize them, great. I would just say get a feel for where they are. Get like familiarity with it. You're gonna get something like this. So now you can see the wave numbers, roughly where to expect them, what kind of description, strong, broad, medium, weak, things of the sort. Some charts have more details than others, and generally just some basic patterns that you should be aware of. So, I mean, that's the gist of IR. I am gonna show you one last website that you can use to practice on your own, and after that we will be finished. So, any questions about anything we've talked about so far? Okay. So I would like to finish with this. I'm going to share the website. And this website is called the Japanese Spectral Database of Organic Compounds. So right over here, Spectral Database for Organic Compounds. Let me see if I can go back. Here we go. So this is what you would see at the homepage. You can go and look at this website on your own. Question is, can you post the websites on the announcements? Yes, of course. I will gladly do that. Thank you. Alrighty. So yeah, the spectral database for organic compounds, SDBS. When you get to the website, just click I agree. And ooh, what's happening here? I guess I've used it too much. Let me refresh it. There we go. Okay, so this is what you should get when you get to the website. You can look up the formula. You can look it from a range of molar masses. If you know the CAS registry number, which is a very specific ID number assigned to every compound, you can type in all sorts of information. But most likely, what I want you guys to do for practice is just look up random compounds like acetone, like acetaminophen, like stuff we've used in lab, and look up their IR spectrum, their spectra, and just practice, right? So let's do acetone for fun. You're going to click search. You're going to get some results. You see, it's the first result right here, acetone. Where it says IR, it says Y. Yes, there is an IR spectra available. Let's check it out. Click it, and you see right there the IR spectrum of acetone. This is from an actual spectrum that somebody actually took of the actual molecule, so you can see exactly what it looks like. Right? So you see here, you have your carbonyl. Let me see, annotating, drawing. Here you have your carbonyl right there at 1700. There's 15, 16, 17. So this is at roughly 1700. If you want to know exactly where it is, you could just find the number, right? So look, it's at 1715 and the transmittance is 4. So that gives you the intensity. So this 1715 is the carbonyl. You can tell me this is at 1715. You can find that right here. Look, you can see the table of the peaks right there. It doesn't tell you what the peaks are. It just tells you what the numbers of the peaks actually are. That should be able to help you. So in the post-lab quiz, I'm going to give you a spectra of one of these compounds. I don't know which one. It could be acetone. It could be acetaminophen. It could be ammonia. Who knows, right? But the point is, I'm not just going to give you that. I'm going to give you some information about the molecule, and you have to tell me what functional groups are there. You might have to draw the missing pieces of the molecule. You might have to explain some interesting phenomena in the spectrum based on certain chemistry rules. So go to this database. I will post it on the announcements as was requested, and go through multiple examples, and hopefully that should give you some practice. So let me try one more. Let's see if we can go to let's do, I don't know, does anybody have a suggested molecule we can look up? You can't do drugs. I already tried looking up drug compounds. They don't show up on here, right? So you can't look up, illicit substances on this. I've tried. Somebody please suggest a molecule in the chat. What else can we look up? Okay, we have a suggestion. I said you can't look up drugs. Like you can't look up like LSD. You can't look up like methamphetamine, right? You can't look up the spectrum of these drugs on this website. Yeah. But suggest something else, something that you use at home, something that comes to mind. Ibuprofen. Perfect. Let's look up ibuprofen. Okay, so there it is. It's the first one because the bottom is an S enantiomer. Let's just look up the actual one. And there it is. You have the structure at the bottom and you have your IR spectra right there. So look, there's a carboxylic acid in here, and you can kind of see a wizard's beard, but it looks like the CH3 are stronger this time. So the beard looks kind of weird, right? Machine Gun Kelly, when he lost against Eminem, the beard is weird. So yeah, this it doesn't always look like the examples. The examples are the simple situations that we show you. This is why I'm encouraging you to go look up your own molecules so that you can get some practice. We look at it and then we justify it. So for example, there's a carboxylic acid in here. Where is it? I'm sorry, where's the carbonyl of the carboxylic acid? Where is that in the spectrum here? Where's this carbonyl? Right here, this one. Where is that located in the spectrum? Where can I find that carbonyl group? 1700, right? Because we've been seeing from just examples that carbonyls are generally at 1700. So look at 1700 and there's exactly a signal right there. And you might say, wait, but you said it was supposed to be strong. Well, it looks stronger than 50%. So I would still call that stronger than just medium, right? Maybe it's medium strong. It's not always going to look 100% like other compounds. This is why they're unique. This is why we do IR. Each compound has its own unique signature. And the question is the CH so strong because there are so many? Yeah, pretty much. You can think about it that way. But we still cannot tell you how many. We just know that there's enough to cause a strong signal because all the CH3s would be emitting that vibration, right? So practice, there's an aromatic ring. Maybe that's why the CH peaks are so strong, right? There's an aromatic ring in here. So look, maybe this is your carbon double bond carbon. Maybe this is another carbon double bond carbon right there. Maybe it's this one right there, right? Practice. Just start reasoning your way through it. Let's do one more and then we'll call it a day. Give me one more compound. Aspirin. Perfect. Let's look up aspirin. Okay, so there it is. Orthoaceto oxybenzoic acid. That is the IUPAC name. All right, and there it is. So look, we have two carbonyls and we have a carboxylic acid. Oh, actually, this is an interesting example here. We have two carbonyls and they are both in different functional groups. So they should both have different wave numbers. So we should expect two carbonyl peaks. So let's check it out. Let's go to 1700. So here's 15, 16, 17. So 1700 is right here. And look, I see one and I see two right there. You see that? Both of those are carbonyl peaks. Because look, we have a carbonyl right here and we have a carbonyl right there. You see that? Make sense? So a question on the post-op quiz might be which one is which? Well, one should have a lower wave number than the other. Which of the two has the lower wave number, an ester or a carboxylic acid? Well, the carboxylic acid has hydrogen bonding, so it has a higher wave number, right? So the lower wave number would be the ester carbonyl. The higher wave number signal would be the carboxylic acid carbonyl. So here we have two carbonyl signals. And then, of course, this would be the carboxylic acid OH. This would be sp3. This might be some sp2 somewhere in here, but it's being blocked by the OH, so we don't even get to see it. You see? And, we have an aromatic ring. So again, this is probably your carbon double bond carbon bond right there. I accidentally wrote an oxygen. Carbon double bond carbon right there. So again, the rest is up to you. Go on this website, look up random compounds. I'm going to pull a few spectrum from here, and I'm going to ask you different questions about them on the post-lab quiz. The post-lab quiz will be 2 weeks from now. So the second day of lab 5, at the beginning of class, we will do the post-lab quiz. The worksheet can be found in the course packet. That will also be due on the same day. So everything is 2 weeks from now. You have 2 weeks to work on this assignment here. Next week, we will meet in person, back to regular schedule. No more Zoom meetings for the rest of the semester. If you have any questions about IR, please come to office hours, schedule office hours. We can meet on office hours on Zoom. But other than that, thank you very much for your attention. I will be posting this video and I will link it on the Canvas. So I will stick around if you have any additional questions. But other than that, the lecture has ended. Thank you for your attention and feel free to stick around. Otherwise, have a good night and have a good weekend. I will see you next week. And there is a pre-lab quiz next week, so make sure you study.
Thanks, Eduardo.